All right, I think I'm going to go ahead and get started just because I can talk a little bit. My name is Chris Kaler. For those of you that are brand new to graduate projects, this is one of our recruitment events as well as our mid-semester presentation. Let me just, there we go. So I'm going to make a few class announcements and welcome everybody that's brand new to the program as a sort of visitor. We will quickly just tell you next week we have a guest speaker from Johnson Space Center talking about spacesuits. Do you know this person, Dr. Nabity? Yes, yeah. Tessa Rundell will be joining us. And then 2 weeks from today, we have Lena Hutchinson from JPL. And reminder for the class, peer evaluations are due tonight at midnight. So please take the time to do that. All the tips and tricks we've talked about are in the form as you're filling it out. So please make sure that you don't forget to do that. Not only do your faculty advisors review that, but your teammates will review that anonymously and you'll get some great feedback. Again, how many of you came as a guest tonight? Just want to make sure we greet you. We're going to bring you a pen, an envelope. We'll try to get you to sign up to the graduate projects course. No, won't do that. But thank you for being here. Just quickly about the course. It's a 2-semester course. You can do it instead of your thesis, or if you don't want to take a bunch of extra coursework, which are the options you have to get your master's degree. You can also take them, well, I skipped ahead here, but it's a real world project. You're going to see that tonight. Students are working on things right now from different stages of their project life cycle. And this is give you a taste of what you can do starting in the spring. It's a 2-semester requirement. You can start anytime. You can take a break. You don't have to be concurrent. You can start in the spring, take it in the fall. You can do it spring 2025 and then spring 2026. It's very flexible. It's hands-on, engaging, and so much fun. You're going to see that tonight. Everyone's had fun. We have weekly lectures, which is typically on a Monday, and then your lab or your project has 2 lab sections per week, roughly 2 hours where you're working with your faculty, getting advice, moving on, and getting your project complete. I'm not going to go through all that, but that's my contact information, kohler@colorado.edu. Please reach out, stop by my office, talk to any of the students here, ask them for their honest opinion of how things are going. We'd love to have you. Registration opens at the end of this month. So we'd love to get you connected. Any questions before we get started? So nice to have such a big room. All right, great. Well, here's our schedule. Series is going to go first. I did have to make a few changes. So we're going to go right into this. Each team has 10 minutes, give or take 30 seconds, and then roughly 2 minutes for questions from the audience, from myself. So with that, I'm going to have the series team come on up. Hold your applause until they're all standing up here. No. This is where we hope that all of the, oh, and by the way, students in the class, this is the audience participation QR code. So again, if you rate every team's performance, not your own, you get a chance to get some extra credit, but the top 2 teams get extra prizes. So I'll keep this up as we go and at the end of each talk. So I'll hand this off. Definitely use the mic. That's the clicker. There's 2 mics here, multiple mics if you'd like. Feel free to wherever you want to go.
Is this working?
Thank you, Professor. My name is Bryce Logging. I am the project manager for Series. Series is an ECLSS project that is environmental control and life support systems that is focusing on developing a novel CO2 removal system for long duration space flight, with one use case being missions to Mars. Just a slight overview of what we're going to go over today. We're going to start with the project intro and organization, going into overview and the follow deliverables for the semester, and then go over a great overview of our progress this semester and the project status looking ahead at the end of the semester and next spring. Meeting the team, we've got some very flattering photos that were taken during our testing campaign this semester. I've already introduced myself as project manager. We also have Jesus, who's the systems engineer, Marjorie, who is the deputy project manager, Senna, the testing lead, Stephen, our data acquisition lead, and then Zoe, the mechanical engineering lead. Looking at our org chart here, it's pretty self-explanatory. You can also see a few names that you may not remember from the previous slide. What's cool about this project is that we also have some undergraduates who are helping us with this research, allowing them to gain that valuable research experience in their undergraduate years. So we have a few of those, a few leading smaller teams for the project, and then a lot of other undergrads helping us with testing and just helping us with smaller tasks, what fits their schedule. We also have a pretty cool project advisement breakdown. Our main sponsor for the project is Boeing, as shown on the first slide. This is really cool to be able to interface with their environmental control and life support department. They are very involved with the project. We have tag ups with them every week, and we're able to kind of bounce ideas off them, get their feedback every week as we kind of iteratively work on this project. So it's really cool to be able to interact with them as much as we can. And then, of course, they're the main project sponsor in addition to the Aerospace Engineering Science Department. And then we have our lovely faculty advisor in the audience right now, Dr. Navity, with the Bioastro Department. In order to go over the system itself, I'm going to hand it off to Marjorie, who's going to explain what CERES is.
Yeah, so CERES is CO2 environmental removal for extended duration spaceflight. So to put the project a little bit into perspective, in Earth's atmosphere, we have about 0.04% of partial pressure of CO2. And in the ISS, they have about 0.4% partial pressure of CO2, which is 10 times bigger. This can cause mild symptoms like headache, dizziness, and confusion. So the goal of the project is to beat the current system that is in the ISS while doing something that is regenerable, survivable, and maintainable. So the scope that was given by Boeing for us this year is to develop and test a low power consumption system for CO2 removal with a focus on the desorption system. So last year's team developed a system, they built the parts. So now we have to test each part and assemble the whole system together to be sure that everything works and also to optimize the system for the CO2 removal. So the project requirements that were given by Boeing are first that it has to be a closed loop with a low amount of consumable and a high regenerability. They want no zeolite, no amine, and it has to support 4 crew members at a partial pressure that is below 1 millimeter of mercury. They also want something that is below 100 watt, and they want something that is operable without any performance degradation for 3 years. This is a little bit of a ConOps that we have for the project. So let's say we have 7 months to get from Earth to Mars. Then we have about 3 months on Mars. And then we have 9 months to go back to Earth. And during this time, we have 4 astronauts that are on the space habitat that breathe about 1.3 kilograms of CO2 per person per day. And where the CERES system is come into play is that it will absorb all the CO2 and either reject it into space or put it back into an enclosed system. All of that by being below 1 millimeter of mercury partial pressure of CO2. The 2 big milestones that we have this semester is, first of all, a test readiness review with Boeing that we have in about 2 weeks. This will present different tests that we want to do for our full system assembly. And we also have the ISIS abstract that we want to submit before the 14th of November. Now I will let Jesus talk a little bit about the full system.
Hi, everyone. I'm Jesus, the system engineer, and now I'm going to talk about what we've actually been up to for what's gone by of the semester. So as a system engineer, one of the things I had to do was develop the system diagram. Beautiful, isn't it? And like Marjorie said, the whole point of this project is to keep our happy astronauts alive, right? So how do we do that? We don't want them to suffocate. So what we do is we remove the CO2 from the cabin atmosphere, and we flow it into one of the components of our systems called the absorber. So here in the absorber, that air will interact with an ionic liquid that will absorb that CO2 from the air, so that then CO2 depleted cabin air can go back into the cabin atmosphere. Now, what happens to that CO2 that's been absorbed onto the ionic liquid? It will be transported into the second big component of our system, the desorber, where in order to remove that CO2 from the ionic liquid, we'll first have some vacuum, so negative pressure to promote that desorption. But if the CO2 is still feeling a little clingy, we also have an ultrasonic transducer, which is kind of the nuance of this project, to help motivate that desorption of the CO2 from the ionic liquid. So once the CO2 is completely removed, it will then allow the regenerated ionic liquid to be recirculated to the absorber, and then the cycle continues. So now I'll pass it to Zoe that will talk more about the absorber and the desorber.
Oh, let me go back. So this, oh my gosh. This is the desorber, and you can see where the desorber inlet and outlet are, and you can see how the ionic liquid will flow through the channels. So that was the bottom plate. This is the full assembly of the desorber, and you can see where the vacuum pump inlet is and the ultrasonic transducer is in reference to the ports. Now, this is the absorber, which has ionic liquid inlet and outlet, as well as a gas inlet and outlet, which is agnostic of each other because you can flow the gas either way. Now, with testing, we found a lot of challenges, and we had to come up with a lot of solutions. The biggest one that we faced this semester was fitting leaks, but eventually we added enough Teflon tape and we tightened everything enough where we finally have no leaks. And another big concern that we have is ionic liquid overflowing from the channels, as well as excess pooling at the desorber outlets. And we do have manufacturing solutions for this for if or when it becomes an issue. Another concern was ionic liquid getting into the vacuum pump. So to solve this, we ordered a hydrophobic membrane that will sit on top of the channels and separate the ionic liquid flowing through the channels and the CO2 in the headspace of the desorber. Lastly, we created a plethora of standard operating procedures to reduce any potential damage we could put on hardware when dealing with the system. Now I'm going to go to Senna to talk about testing.
So all the mechanical concerns that Zoe has mentioned stem directly from our testing operations, which is divided into two different phases. In phase one, we are focused on system verification, where we're making sure that our system functions as intended. In phase two, we do system flow rate test, and finally a thermocouple heat transfer test to make sure that the temperature between the inlet and the outlet flow are even. And so all of these tests are to help make the system reliable so that we can go into phase two of our system, where we are going to optimize this. And now I'll pass it to Stephen for our data collection.
This thing working? Cool. All right, so all of that testing means we have a lot of data collection that we also need to do, since that is required to verify that our system actually meets requirements. Is this? Oh, nice. Okay, so our system uses a combination of LabVIEW software for data handling and processing, as well as National Instruments for our hardware for sort of collating all of the data from our various sensors. And on the right, you can see a system diagram of all of our sensors. The sensors come from a variety of vendors, and we have a lot of them. Most of them are for characterizing our gas flow, but we do have a couple in the ionic liquid because that does affect our absorption capabilities, and those go into multiple hubs, and they all eventually go into our lab station. So going a bit more into detail on our sensor suite, we have, you can read the table, but we have a lot of sensors in the gas flow, which are all of these guys. And they characterize the gas flow in order to characterize our CO2 removal capacity and our mass flow. And the reason we have oxygen sensors down here, which might be a bit weird, is for fault detection and for detecting any sort of unforeseen interactions with our ionic liquid. And since having oxygen is also important for not dying. The thermocouples measure the temperature of the ionic liquid because the temperature also affects our absorption and desorption capabilities. And with that, I'll pass it back to Bryce to finish us off.
Yeah, thanks to the entire series team. Hopefully everyone was able to get a pretty good grasp of the project going forward and what we have left to accomplish. I'll touch on that in a moment as well. We already touched upon some of the mechanical concerns that we have faced during this project, but we also have severe project challenges that we are facing. One that is pretty prevalent along most graduate projects is team member training, onboarding, and communication. As a project manager, this was my biggest challenge, trying to integrate communication into the team, making sure everyone's on the same page. 5 out of 6 of us came into this project knowing nothing about it at the start of this semester, and we're required to be very quickly brought up to speed on the project. So that obviously took some time and learning and a lot of dedication from every one of us. And then in addition to other challenges such as lab space scheduling, testing time allocation, and then concerns that we are facing during our testing campaign, such as insufficient system performance and component faults during testing. These are standard through testing. That's why we do testing, to make sure things work. But of course, that still needs to be factored into your risk for the project. As for the project status, we already elaborated on our objectives for fall 2024. That should say spring 2025, my apologies. But for the spring semester looking ahead, the ICES paper that we mentioned so far, this will be actually written next semester rather than just submitting an abstract and then hopefully going to this conference to present this paper. In addition to alternative desorption testing, testing out other systems such as microwaves other than the ultrasonic transducer that we use, in addition to full characterization and optimization of our assembly. Thank you, everyone, for taking the time to listen. If there are any questions, please let us know. I know we're a bit short on time for questions, but my email is also up there if you have any interest or questions for us.
One question.
What was or how's the ionic liquid made? Like, what is in it?
So an ionic liquid is essentially a liquid salt, basically, and it oh, sorry. Can you hear me? Can you hear me fine? Yeah, so it's a liquid salt, basically, and it has specific chemical groups that essentially allow the CO2 to bind to it and form a complex that can be easily unmade. Easily.
Well, thank you very much. That's what I think it was off. Okay. And for those of you that I did not tell you earlier, the top button does give you the ability to kind of highlight what you're pointing to. So
Yeah, we'll just pass click.
okay.
Yeah. Got it.
All right, are we ready, Chris? All right. Hi, everybody. My name is Chase Ruprecht. This is Andrew Cabos, Thomas Dunnington, and Owen Craig. And we're team ARIS. We're the Autonomous Rapidly Reusable Atmospheric Sampler. And our project is in collaboration with CU INSTAR, which is the lab just across the way over in the SEEK building. They're the Institute of Alpine and Arctic Research. So the project motivation, this project stems from the motivation of sampling the Earth's atmosphere. INSTAR is doing some work in the Arctic to understand our atmosphere. If we look at existing atmospheric models, here's a model of methane transport in our atmosphere. You'll notice a couple things. First off, we have a lot of measurements from high above the ground. And second, we have a lot of measurements from really populated places. So you'll notice there's not a lot going on in Antarctica or in the North Pole. And we need to understand these methane concentrations to predict climate change and understand our atmosphere. And you'll notice what's missing is the boundary layer measurements in extreme environments. The boundary layer is defined as the regime from the surface up to about 1,000 meters above the atmosphere. And that is what we are interested in studying. So let's talk about how INSTAR has tried to do this in the past. So here is the Greenland ice sheet, eScript. And in the past, they've erected tall towers with sensing equipment in order to understand the atmosphere. They're measuring trace gases and methane concentrations. You can imagine that it's pretty difficult to erect tall towers on an ice sheet, and it's not very valuable scientifically because you can't get very high off the ground. You can't get far into the boundary layer. And so in more modern times, INSTAR started to use UAS as a solution to measuring the Earth's atmosphere. So here we have a Black Swift S2 UAS. This is a 10-foot wingspan drone. And they've used this system to fly around the Greenland ice sheet and measure the atmosphere. There are also challenges with this system. As you can imagine, it's very complex. There's a lot of moving parts. A lot of things have to work right in order for this system to successfully complete its mission. There's also extensive ground equipment necessary to maintain these systems and use them in the field. You've got launching systems and transport systems. All of these added together add to just a lot of complexity. That's not even to mention some of the logistical complexity. This is the LC-130. This is the aircraft that Instar uses to fly out to the Greenland ice sheet. There's a little clip on the right of what it looks like inside of there. A flight on one of these aircraft costs around $300,000. And to get all of that equipment that they need to monitor the Earth's atmosphere, it costs about $500 per Black Swift S2 UAS flight. That's just too expensive to scale up the science. So what if there was a better way? Let's look at the ConOps for the autonomous, rapidly reusable atmospheric sampling system. We want to deploy a system in the environment that generates its own power. It will also use sensors on board to monitor the environment and make a go, no-go flight decision for a tethered balloon. If it decides that the environment is suitable, it will heat up the balloon and lift a 1 kilogram payload to 500 feet above the surface of the Earth. It will then take its scientific measurements. After that, it'll retract the balloon back to the system, compile and compute all of that data, and then transmit it over a satellite network to a cloud for all of us to view on our computer. We imagine a future where we might have tens of thousands of these sensors all across the globe, updating this global monitoring network and understanding our atmosphere on a sub-daily level. I'm going to hand it off to Thomas now.
Yeah, so that ConOps has a very, very broad scope. So what we've kind of tried to do is narrow our scope for the project for this year. So we're trying to design what we're calling the minimum viable product, which has a reduced set of requirements. Mainly, we just want to be able to live 1 kilogram payload, and that's going to be the atmospheric sampler. And we want to reach just an altitude of 100 feet. And this allows us to kind of simplify the project and make it a bit easier for our scope. And here's a picture of an example of what they flew on the Black Swift drone of the air sampling system. Something similar to that will go on our system, but we're just designing the actual method to get that system up to altitude. So in terms of project organization, we're a pretty small team. We just have 3 faculty advisors. We have Kevin, who's our engineering advisor, and we have Ben, who's our atmospheric sciences advisor, as well as Tyler, who's our climate sciences advisor. And then for the students, there's only 4 of us. We have Chase, who's our project manager. My name's Thomas. I'm the software lead. We have Andrew, who's our electrical lead. And then finally, Owen is our mechanical lead. So in terms of what we're doing this semester for our fall deliverables, the main thing is we're trying to model the performance of various different hot air balloon designs and see what the performance is for them if we vary the mass of the balloon, how big it is if we size it up, and what the temperature is on the inside, and kind of just produce different models to see how they perform. And to help inform those models, we're also conducting lots of experiments. So the image here is our test bed where we have ripstop nylon, which is the material we're planning to build the balloon out of, in just a small volume with a heating element inside. And we're measuring the temperature inside to characterize how hot we can get it, and also what the decay curve looks like when we turn the heater off. And lastly, all of this is meant to provide a cohesive report where we're going to detail whether or not this is actually feasible. So for our preliminary model, here's an example where we use a 2-meter radius balloon with 25 meters cubed volume. And we assumed a maximum uniform temperature of 90 degrees Celsius and a heat transfer coefficient of 1. And you can see that we get up to about 150 meters. And you can also look at the decay curve where we start at 90 and go down. And this is a balloon that's actually heated on the ground and then just released up into the air. So that decay curve is while it's released and rising. And so our experiments are really meant to kind of characterize what that decay curve looks like, and also to tell us how hot we can actually get the temperature inside the balloon.
All right, so now once we had our preliminary models, we kind of needed to design experiments to kind of validate and verify these models. So first off, what are we going to design this experiment to do? First off, we need to define the ultimate question we want to answer, and that's how much lift can be generated for how long. This can be defined with the buoyancy equation, which is related to the density of the air inside the balloon, which is related to the temperature of the balloon, of the air inside the balloon. And so that raises the question, how hot will the balloon get and how long will it stay hot? For us to figure that out, we created an experiment where we take a balloon, which is represented by the square, like a balloon analog. We put a heater inside of it that gives you heat into the system. And then you can take and assume that the radiation from the system is negligible, or the radiation into the system is negligible. And then you want to characterize the heat transfer out of the system so we understand how hot our balloon gets and how long it will stay hot. So how are we doing that? Our experimental test bed is basically an 18 by 18 inch system that is a cube that is enclosed in ripstop nylon. And we conducted 3 different experiments. The first of which is just with the nylon. The second of which is the nylon is covered in a basically tape that makes it more airtight, just to see if reducing any air escaping from the system improves performance. And then also that system is then covered in an insulation so that we can test if adding insulation to the system, or basically reducing our heat transfer out of the system, helps improve the how much and then how well it improves the heat transfer out of the system. Cool. So what did we get from this? First off, this is the first test where it was just the ripstop nylon. You can see that the curve drops very fast and converges to ambient temperature. This blue line is ambient temperature. There is some offset in the thermocouples, but it gets down there pretty quick. So we don't hold a lot of temperature for very long. So that's not great. Now adding that kind of airtight barrier, we get a little bit slower of a decay over this time. However, it still converges to that ambient temperature very quickly. Also not great overall. However, then adding insulation, you get a little bit slower of a decay, and it converges to a much higher temperature over time. This is what we want. This is what we were looking for. And kind of comparing those results together, you can see that this purple line, test 4, with that insulation is very good. This kind of informs the decision that we should be looking into kind of reducing that heat transfer coefficient. Now I'm going to hand it off to Andrew.
And so using this experimental data, we were able to cook up some models quickly. And the first model that were multiple models that we did equations of motion, just how far we're able to estimate the trajectory of the balloon up into the sky. The first model that we did was a more conservative model where we took the temperatures directly from the backsides of the decay curves, and we're able to just find directly buoyant forces and extrapolate them up into a curve like this. And then a little bit less of a conservative model, we were able to model height over time with taking the temperatures and converting or finding a heat transfer coefficient using those temperatures, and then scaling up those heat transfer coefficients to a full-size balloon, again, to model a full-size balloon. And so what we found from this is that the heat transfer coefficients go down as is to be expected with more insulation. And with our more conservative model, we were able to reach a height of 150 meters with an insulated full-size 2-meter radius balloon. And with the less conservative model, we were able to see 325 meters at the high end. And that's just an image of our test bed heating up. And this directly leads into some of our concerns. Our concerns are mainly that these models showed feasible numbers when the balloon was completely insulated. When it was less insulated, it did not reach quite those heights. So we have to look into materials. And then we have some concerns with heating elements, being able to completely increase the temperature within the full-size balloon to an adequate point. And additionally, we have some longer experimental times reaching steady state generally takes quite a bit. And so moving forward from here, we have some additional experiments to do and some knobs to turn. We have to do experiments targeting heat transfer and how that can change with different materials, masses, and volumes of the balloon, which we've already started to do, just so that we can adequately quantify whether or not an electrically powered hot air balloon is something that is feasible to be used in the use cases that Instar requires of it. And if not, we are also open to exploring off-ramps to solutions like tethered drones, which are still quite significantly simpler than that which Instar is currently using in their testing. And that's it. That's all we got.
We don't have any time for questions, but nice job. And I'd like to bring up the next team if we could. That is Igloo. Again, please participate in the audience participation. Feel free to get some more pizza. Just be quiet.
Hey, Chris.
All right.
Come on, can you hear me?
Yes.
Yeah, I had a question for the last time. I threw it in the chat.
Okay, great. Thank you. All right. Who's going? Who's leading?
Okay.
Okay. All right.
Hi, my name is Lynette Chapman. I'm the Deputy Project Manager for the Igloo team. Our project manager, Tucker Payout, cannot be here today. So he recorded his slides for you. And I'm going to go, wait, how do I go back? Okay, I'm going to go back and we're going to get this started and he'll present for you here. Wait, how do you play? Is it not playing? Yeah, how do I? I mean, I can, it's not working. I can't get it to, should I just say it myself?
Yes.
Okay. All right, so this is Tucker. You can see him in the corner there. He was presenting for you. So we're just gonna go over our agenda. That's the project overview, project organization. We have our deliverables, team progress, our project concerns, and then we'll leave some time for questions later on. Oh, sorry. And so I'm going to talk about the project overview. So the motivation of our project is to enable safe lunar and human operations as part of a larger program for future missions on the moon. The purpose is for this project is to really design a lunar, support lunar operations on the surface. And to do that, you need a really solid lunar habitat. And Igloo is the Igloo architecture is intended to advance the state-of-the-art lunar habitats on the moon. And our goal for this project is to design a conceptual design for the Igloo or lunar habitat. We're also going to be building a full-scale lunar markup next term, and we are doing some iterations to the mockup that's currently in the high bay now. And then we are going to perform human factors testing for both semesters to test reconfigurability, radiation safety, and other general human factors within the habitat. And I'm going to give it over to Charlie for the concept of operations.
All right, so here is our ConOps as it stands right now. So our habitat and our crew are going to take two different paths. First off, our habitat's going to launch on a cargo launch vehicle. We're going to land on the lunar surface and then configure from a sort of vertical launch configuration into a horizontal configuration for the crew to enter. After that, our crew is going to launch, transfer from Orion to the human lander system, land on the lunar surface. They're going to conduct their science exploration, other daily activities, and then they are going to transfer back to the Orion and back to Earth. And our project is really focused on this part that happens on the moon, keeping our crew alive, happy, healthy, productive, that whole thing. And now I think I'll pass it to Sam for our functional objectives.
All right. Yeah. So what you see on the screen here is our top 5 functional objectives that we derived. For those that have taken Dr. Klaus's Space Hab class, you're probably wondering, well, Sam, where is our keep the crew happy, alive, healthy, productive? Well, those are going to be our level 1 functions that are directly derived from our functional objective 4, which is making sure that the crew can survive in space for 30 days with 7 days contingency. So don't worry, it's not forgotten, it's just hidden. That's all I have. I will pass it to over there.
Thank you, Sam. Appreciate it. Everyone, Sam, he's been growing that mustache out for 3 years now. So give him a big round of applause. I'm going to talk about the organizational chart. I thought I was going to introduce everyone, but for time constraint purposes, I'm not. I'm just going to introduce Boeing, our customer, our senior manager, Rick Heeb. Obviously, Tucker's not here today. Lynette, our wonderful deputy PM. Sam Lisak, thank you, systems engineer. And Charlie Preeb, technical director. Jonathan Abrams, our financial manager. And Ben Halfant, our safety manager. And I wasn't going to do this today, but his wife's here, so give it up. NASA astronaut, Army Ranger, experimental test pilot, Colonel Jim Voss. He is our professor and senior manager. Thought I'd embarrass you a little bit today, but so that is Team Igloo, and I'll pass it off.
Hello, my name is Noah. So just like Ceres, our main corporate sponsor / customer is going to be Boeing. They mainly listen to and provide feedback to our large presentation deliverables. So this could include design definition reviews, senior management meetings, and requirement reviews. And then more of our day-to-day support comes in the form of, as Ken wonderfully introduced him, Colonel Jim Voss, and Rick Heeb, who serves as our senior manager. And they are within the bioastronautics department, which is where our project is housed. And then finally, of course, we could not do this project without the support of this lecture class, the graduate project class led by Professor Kohler and Joey Shai. So now I'll pass it off to Jonathan.
Thank you very much. Hello, everyone. I'm going to discuss the subsystems that are included within our habitat. First of all, we have the structure subsystem. This provides the boundary of the habitat and also maintains a pressurized environment within to keep the crew alive. In addition, we have mechanisms. This deals with all moving components within the habitat, especially the hatch design, which is a key point for Boeing this semester. Next, we have thermal subsystem. They're responsible for ensuring a thermal equilibrium is maintained within the habitat, tracking all heat flows into and out of, and ensuring that it is a livable environment for the crew. After that, we have the environmental control and life support subsystem, ECLIS. They're responsible for maintaining all the biological needs of the crew, keeping them alive. We have crew accommodations, CA. They're responsible for providing all the extra equipment to keep the crew productive, happy, and healthy. We have payload accommodations and EVA, extravehicular activity subsystem. They're responsible for providing the equipment to allow the crew to perform science and maintenance activities, such as EVA suits. We have power subsystem. They're responsible for generating, conditioning, and providing electrical power to all the necessary components and to the habitat as a whole, making sure everything is properly functioning. Then we have command and data handling. They are responsible for sending commands and receiving telemetry from all the components within the habitat, and then ultimately forwarding that to ground via the communication subsystem, which is responsible for handling voice, video, and data communications between the habitat and ground. And finally, we have human factors, which is responsible for ensuring that the habitat maximizes the human efficiency and operability of the human within. And next slide, please. Next, we're going to go into the deliverables.
I'm Lindy Bishak. I'm the crew accommodations lead on the team. For the fall semester, we have 7 deliverables. The first 2 we've completed. They were meetings with our customer, Boeing, kickoff and a technical interchange meeting to cover the scope of work and agree on our concepts. We're currently in the design and build phase. We are working on engineering documents, the conceptual design, including CAD drawings, and we're starting the build of our mock-up. Finally, we'll end with human factors testing, as mentioned earlier, and additional meetings with our customer.
Hello, everyone. I'm Roop, and I'll give you an insight on conceptual design of the habitat. So we are designing the habitat, which is optimal for 4-people crew for 30 days mission with 7 days of contingency. and the habitat will have a 15-year of operational lifespan. For the inside of the habitat, we are designing reconfigurable spaces for various operations such as like science, living, and radiation protection. A good example would be that our workstation turns into safe haven in case of any solar radiation anomaly. The habitat will support EVA operations and all astronaut-related activities. And I'm going to pass on to Kevin to give you more in detail design overview.
Hi, everyone. I'm Kevin, structures lead. So now we know what we want to achieve, and the next step is figuring out how we will achieve that. And a big part of that is the layout design. And that means not only the conceptual layout design, which will achieve our conceptual objectives, keep the crew alive, happy, healthy, productive on the moon, but also designing something that can be replicated or translated to our medium fidelity full-scale mockup in the high bay. So on the left side here, you can see the CAD model of the external structural layout design, and then directly below it, a side cross-section view of kind of the overall layout. So in this design, there's a separate habitat and airlock module. That works. Habitat module is on the left, and the airlock module is down here. So the habitat module is pressurized, and that is what makes up our total pressurized volume of 90 cubic meters. And as well as our habitable volume, which is the volume that the astronauts can actually use, of 20 meters. And both these values are nominal or above based on heuristics for the number of crew and the duration of the mission. You can also see there's 3 different hatches. On the left, there's a docking port for rovers and resupply vehicles. There is an inner hatch that goes from the habitat to the airlock, and then an outer hatch from the airlock to the surface to enable extravehicular activity of the astronauts. And you can also see above and below the habitable volume, as well as to the right, there's storage for different subsystems, as explained so well by Jonathan. And now I will give it to Garrett for mechanisms.
Hi, so one of the very specific requirements of Boeing is to build a 40 by 40 hatch that slides and latches from the frame. So we plan to satisfy that requirement by having our hatch slide via ball rollers, and it's going to latch from the frame with electromagnets.
Hi, I'm SB. I'm going to be talking about the mock-up. So to keep it brief, essentially on the left-hand side, we have what we got at the beginning of this semester. On the right-hand side is where we're transitioning to. And so you'll see that there's 2 hatches and a haven. Those 2 hatches and haven are specific to our project and what we're going to be adding to it. The mock-up build also was reoriented on the layout inside, where SQ means sleeping quarters, exercise means where they work out, and WMS is basically their bathroom. And so we reorganized it so that way there's more happiness in how they stay in the mock-up, which is physically shown on the right-hand side with a little bike making up our workout station and the main walkway. And now I'm going to be passing it on to the next person for time constraints.
So our human factors lead, Lindsay, wasn't able to make it today. I don't think the recordings and things are working. So I'll just talk about this. This is our human factors testing. We'll be doing that, conducting that November 12th to the 22nd. If anybody is interested in joining and being a test subject, you can take a picture of this QR code right here. And we'll be testing the hatches, the equipment, the reconfigurability, the safe haven, and the hatches as well.
All right. Hi, everyone. My name is Ben, PA EVA lead for the team. Going over some quick project concerns. We're currently monitoring the schedule for the project. We're in the process of transitioning from a research and design phase over to a low to medium fidelity mock-up build that we're building in the high bay currently. We are trying to finish that mock-up build by the end of October and are still currently procuring materials. So we are making sure that we aren't going over our budget or anything like that.
And again, we have our QR code here if anybody wants to scan that for human factors.
Thank you.
You all keeping track of your time? Okay, cool. All right, well, I don't think we have any time, right? Oh, yeah, right on time. Yeah, sure. Okay, great. Thank you. Nice job. The next presenter is actually me, but I'm going to go super fast and then we'll have Maxwell come up. But okay, great. We're all having kinds of fun here. Hold on a second. Dennis Akos here on campus has a project that he's proposing for the spring, and I'm just going to quickly go through that. I'm not going to go through his bio, but he's an instructor, faculty member here. And basically, he wants to develop a project that utilizes or enhances this Guardian real-time or near real-time system to basically detect or give advance notice for events catastrophic events that could be happening on the Earth. And doing this with a GNSS system and what's built into an Android phone, he has this idea of what could we tap into that 1 to 3 billion Android devices out there, even though the data may be of a lower quality, to be able to help supplement this system. So just a quick overview of a project that we're going to try to start in the spring with Dennis Akos. So that's that. And that's more for those students that are here today looking for a project in the spring. All right, with that, we're kind of caught up again. Maxwell, would you like to come on down? You're all doing a really great job, by the way. Yeah. I see some of you are practicing public speaking skills.
How do we go back a slide?
The button on the bottom. But I was using the Zoom controls. So now I should work again.
Sweet. Okay.
Okay.
Before I start? Okay. Okay. Hi, everyone. My name's Anna, and this is the Maxwell mid-semester presentation.
All right. I'll be going over the mission overview. Oh, could you go to the next? And then the next slide. Okay, so what is Maxwell? Maxwell is the multiple access X-band wave experiment located in LEO. It is a 6U CubeSat that's built, tested, and designed here at CU. It is scheduled to be completed by 2025, and some of our main mission objectives are to test the on-orbit CSAC performance, to demonstrate the high-rate communications with CDMA, to characterize the performance of the T-Dagger antenna, and to demonstrate our student-built ADCS.
All right, now moving into the mission ConOps. So for phase 1, we have our ejection and LV separation. For phase 2, we have our commissioning and deployment of our solar panels and UHF antenna. Phase 3, 4, and 5 are all of our mission objectives. Here, 3 is our communication downlink and telemetry. We also have sun point charging. Phase 4, we have our CSAC experiment, and phase 5 is our T-Dagger deployment. And then phase 6 is our deorbit and end of mission.
I'm going to be talking about the top level requirements. First, Maxwell shall download 150 MB of data at 10 Mbps during 1 pass at X-band. Then it should downlink 15 MB of CDM data at 1 Mbps in the presence of other narrowband signals in the same frequency. Then it should deploy the MMA T-Dagger antenna on orbit, and it shall characterize the Allen variance of the chip scale atomic clock on orbit.
Hi, I'm going to go over the team organization as well as some of our stakeholders. Maxwell has 5 stakeholders: the Air Force Research Laboratory, UNP, Blue Cubed, MMA Design, as well as CU Boulder. The team itself is split into 9 different groups, comprising of enrolled master students, undergraduate students, some volunteers, as well as a couple paid positions.
Coming towards the semester goals, what we are trying to do this semester, after a tentative cycle, we finally came to the conclusion that we are going to be launching next year, and that is what we are aiming for, starting with a critical pre-integration review this fall 24 and moving forward with the pre-shape review by the AFRL. The tasks that are aligned for this semester include the complete charge cycle test that needs to be completed by the end of the semester, long-range communications test, followed by the command execution test, ADCS verifications test, and the day in the life test.
All right, next we're going to run through the different subsystems and give you a brief update on kind of where we are and what we're working on. We're going to start with my subsystem, which is command and data handling. Right now, we're primarily working on the command execution testing, which is basically verifying that we can communicate and control the spacecraft and subsystems. We just wrapped up our CET3, which is primarily focused on the attitude determination control system. And next, we're stepping into CET4, which is communicating with our payload, and then stepping away from hardline communication to actual over-the-air radio. And then we're also supporting various other systems with our day in the life testing, and then communication and charge cycle testing.
Yeah, so the communications sub-team this semester has been really focused on the development of our ground station. This is located over on main campus at the Colorado Space Grant. And we're doing this in order to complete our simulated comms test, like we was talking about, is going to require over-the-air testing between our spacecraft and the actual ground station. So we're hoping to complete the simulated comms test early in November. And afterwards, we'll start pivoting our focus towards continuing to develop the ground station, but adding operational capabilities to support the mission after we've launched.
So I'm Boston. Our updates that we made were we made a lot of CAD changes to our CAD structure, right? As we start testing stuff, we start putting stuff together, we realize the stuff doesn't work right. Things don't fit, the holes don't line up, and things don't work. So we've made a lot of CAD changes, both through integration testing, as well as just by looking around the CAD really carefully, like using section views and looking at all the holes. We start finding weird problems that holes are 10 thou off from where they're supposed to be. And the semester plans are, we got to order the flight model. That's really important when you order the metal structure. It's thousands of dollars and it's really hard to modify after we order it. So it's really important that we order a flight model that's actually able to go to space without significant modification in the aerospace machine shop. We also need to finish the final analysis of the structure to make sure that it won't break up either during launch or in orbit. We need to fabricate miscellaneous flight and test fixture parts to assist other subteams, as well as prepare for the PIR presentation, which will be at the end of this semester and is critical for us being able to actually go to space.
In the assembly integration test world, we have been able to verify any design changes made to our satellite by 3D printing different parts and incorporating them into our assembly dry runs. We have revised our assembly procedure document to reflect new changes and completed thermal chamber testing of our UHF antenna. For the rest of the semester, we plan to finalize our assembly procedure document, and then we are preparing the master equipment list, and as well as testing our solar panel deployment mechanisms and getting ready to fabricate all of our wire harnesses.
So for the ADCS team, some major updates for the semester. We finally got the GPS board integrated into the FlatSat. We did a GPS antenna test to make sure that the placement of the antenna on the flight model is both spatially correct and won't ruin reception of GPS because we need that. We also made really good progress on the flight mode testing of all the commands that we need to send to the ADCS system from the ground. For the rest of the semester, we have some more software integration of the GPS system that needs to happen. We're also going to integrate the chip scale atomic clock, which is one of the main points of the Maxwell mission. We're going to finish integrating all the remaining hardware elements, and we're going to document everything.
Hi, everyone. I'm Austin, and I'm going to talk to you about the PLDC and some of our electronics hardware. So our main update for this semester is we got full communication between our command and data handling and our payload data computer. So that was really great. We went through, we looked at all the individual boards, we solved the errors, and we got a ping to go through. So with all of that being done, we're now looking at our semester plans, which is just rounding out those scripts, getting everything for CET4, and making sure that our payload can communicate properly with our CDH. I do have a second slide here because the second thing I want to talk to you guys about is electronics hardware. On our satellite, we got lots of boards that we build, lots of boards we use. So we've been able to get at the CSS, various breakout boards, and the EDCS, but we need to build the flight board. So this is where it's advertisement time. It passed the ad block. So there's a nice big QR code up there. If you're interested at all in building and testing circuits, go ahead and give that a scan, send me an email, and I'd be happy to introduce you to the rest of the team. Thanks, everyone.
On the system side, we've been in the middle of coordinating with sub-teams to confirm the power, pointing, and data budgets, and documenting the plans for X-band radio and RF hardware, and also making a list of what all the requirements will be. Writing is in progress for the mission ops plan. We finished the day in the life test procedures and finished UHF ground data documentation. For the rest of the semester, we're working on verifying subsystem requirements and writing the mission ops plan. So that includes the ConOps, outlining the anomaly resolution and the flight rules, and then finalizing the link budgets, power budgets, pointing budgets, data budgets, all that good stuff, and also documenting the X-band radio and RF hardware operating software, networking system, and couple UHF ground data documentation.
So I'll briefly cover our project concerns. As you can see, a common thread through all the different sub-teams is software development and debugging, because it's kind of hard to quantify like how much time debugging software is going to take. And something we're doing already to mitigate this is we brought on 2 new members that are going to help with all of that. If we go to the next slide, we'll see that the comms, again, this has been a common thread through all of the different teams, but student turnover and onboarding new people has been kind of took a big chunk of time out from the first part of the semester. So now that that's done, we'll be making good progress there. And for structures, we might need to modify the flight's structure a bit in the spring semester and kind of with that, thank you. And if we have time for questions, please.
We do have time for questions. So, any questions? Yes.
I have another question. If nobody has any questions. In regards to like the X-band radio, I saw there was a bunch of tests with the UHF frequency at 437 megahertz, but is there any testing done at the 10 gigahertz X-band, or is that done by a separate party?
There will be some X-band testing that we're looking at doing over the next semester or so. Part of the problem with that is we're looking at where we're going to be actually using our or what ground station we'll be using for X-band, since it's different frequencies, different hardware is required. And so we were hoping to use the X-band ground station that's currently being built on the roof of the Aerospace building, which would make it super easy to test. We're currently working with CCAR support to figure out if that's going to be a feasible option. But to answer the question, yes, there will be some tests. It will just be potentially less robust than what we're doing for UHF.
All right, nice job. Thank you very much. All right, we're down to the last 2 teams. Formats.
You see the one for forward and back, and then that's the other. Yeah. Hi everyone. This is Ansh. I'm from SwarmX, and this is my team: Anantha, Maxine,
Wesley, and Gotham. And today we'll be talking about SwarmX. First, in the beginning, I would like to thank Dr. Palo and all the other people who have helped us make this project real. So what is SwarmX? SwarmX is short for Space Weather Atmospheric Reconfigurable Multiscale Experiment, and it's funded by NSF. We're sending three EU CubeSats, 10 into 10 into 30 centimeters in space, and we're trying to take some measurements, and we're trying to demonstrate formation flying. And we're working with 5 other universities: West Michigan, Olin, South Alabama, Stanford, and Georgia Tech. Our mission objectives for this project is, for science, we're trying to take some measurements for electron density and mass density of neutral atomic oxygen atoms. And we're trying to find a correlationship between these 2 density features and trying to figure out their characteristics. For engineering side, we're trying to demonstrate formation flying, and we're going to use propulsion to demonstrate different types of formations, such as string of pearls and orbital formations. And most importantly, for education, we're trying to collaborate with other universities so that we can expand CubeSats more and get real life experience. The timeline for this project is we're expecting a 5 months primary mission and 3 to 4 months of extended mission. In this mission, we're going to do formation flying, and we're also going to take some measurements of the atmosphere. Some of the principal requirements over here are listed down. 2 of the most important principal requirements of this project to approximately 8.5 months. And our project organization, since we are working with 5 other universities, it's a big team, and each university has a different role to play. And we're only 5 people, but we have a big team, and we're looking for more people to join us. And I'll pass this to my friend.
So there are a lot of subsystems in SwarmX, but we'll be discussing about the things that we 5 of us are dealing here and kind of upgrading to the next level in the fall 2024. The first thing is communication subsystem. So as you have heard from Ansh, it's like 3 CubeSats at the same place with the same frequency and at the same time. So you need to build something different to kind of communicate with each of them differently. We have a packet structure that we are developing, and we have implemented this on our command and telemetry portals, where we use this for communicating discretely with different satellites from different ground stations. So yeah, this is the packet structure that you see here. We kind of organize the packets in a way where we can transmit and receive information discretely. Next slide, please. And this is the complete setup of the communication system and ground segment, where you have multiple softwares running, and you have cool antennas, and you talk to 3 CubeSats that are in the same place. Right now we are in the process of setting up the ground station and getting it operational, and we would like to complete the wireless testing of the complete command sequences for both the other satellite, Maxwell and SwarmX together. These are some testing pictures that we have from the ground station. So one that you see on the rightmost is the place where we kind of had our, it's on top of DLC. We go out there, we set up our entire system outside the rooftop and try to communicate with the satellite wirelessly and make sure that we get commands through and also the telemetry from the satellite subsystems. I'll hand it over to Wesley now.
All right. Yes, I'm Wesley, and I'm in charge of working on the software for SwarmX's electric power system. This semester was kind of a transition phase for this subsystem, because prior to this semester, it was developed by the University of South Alabama, but their team has reached a point where they're ready to transfer it over to us. And so they sent us their code this semester, and we've started working on it. Currently, we're working on making the electric power system talk to our command and data handling subsystem so that the EPS can receive and execute all the commands that we need it to. Once that's done, we're going to run a command execution test to verify that all of the commands are implemented correctly and that EPS can do everything that it needs to do. And then once we've got the software into that state, we'll be ready to integrate it with a mock-up of our satellite called a flat set to advance to the next stage of testing.
All right. Hi, everyone. I'm Maxine. I work on the science and instrumentation team on SwarmX. So for this semester, we're taking a look at completing the flight unit acceptance test for all of our sensors. The SwarmX CubeSat is equipped with a Langmuir probe, a 5PEX sensor, and a magnetometer, which are all equipped to measure the ion density in both the equatorial ionization anomaly and equatorial thermospheric anomaly. So in order to prepare for pre-integration review next semester, we are looking at safe to mate testing for both the iSense power boards, which control the Langmuir probe and magnetometer, as well as the 5PEX boards. And so we're looking at making sure that these boards are able to be integrated properly with everything else and checking out that everything with the pins and all sorts of electronic connections are working properly. For this semester, we're also looking at something called the minimum communications test for all three of these sensors. I'm currently working on the Langmuir probe test, and that's just checking to see if we can send commands to it and verify that all of the functionalities can be performed and the requirements can be verified. We also have to do the same safe to mate test for 5PEX as well as the minimum communication tests, and the magnetometer needs its own minimum communication tests. And then once those are complete, we can finally move on to the instrument deck full assembly, where we will decide what fits best and make sure that everything is going to work properly within the volume of the SwarmX CubeSat.
All right, I'm Gautam. I work in structures team. So what we are working is designing flat set and fabricating it. Flat set is nothing but a flat plate and stacking up all the components on it for testing purposes. And also we are updating assembly instructions after first dry run that happened in the last semester. Dry run is nothing but 3D printing the model and checking, measuring all the dimensions and testing the assembly. And we also designing the MGSE, which is nothing but mechanical ground support equipment, which is like a phone holder, if I would like to say, like to hold the SwarmX CubeSat and helps us to work on it while doing assembly. And what we are looking forward to is like conduct FEA and decide wire routes. Small things will make bigger problems. So wire routes are one of our main issue, and we have to figure out how to stack them and 3D print the components for next design review. Next slide. Moving to thermal, and again, that's me. So, one advantage of grad projects is you can work on what you know, and also you can work on what you are interested. So I'm also working in thermal team. We are making updates in existing thermal model from the last semester regarding the updated CAD model. And what we are looking forward to is to conduct thermal analysis on both hot and cold scenarios, and get a high fidelity model for future semester and for future people. Next slide. So these are some general challenges we faced, which are onboarding and getting familiar with documents. There are so many documents to go through, and communication within team and organization. If you see, you can see whole United States of America over there. So it's really diversified, and underestimating the tasks and also schedule shift, which changes your task schedules. So all these challenges contributes to delay and make it difficult to complete your tasks on time. Going to next. Thank you everyone for being here, and thank you Dr. Pelo for being here. Thank you James, Professor Nabdi for being here. Hope you guys enjoyed. Peace out.
One question. Right, answered all their questions. Great job. Thank you very much. All right, last but not least, we have one more team presentation and we're right on time by design. While they're coming up, I do want to again thank our faculty members for being here. Appreciate you coming and participating. And I'm also looking for a few helpers to take the pizza boxes after this last presentation to the actual dumpster. Don't dump them anywhere but that. So, okay. Yes, sir.
Thank you so much. Brian, right here. Awesome. Hello, everyone. We'll be finishing out the day. I am the project manager for the Ultimate Jump. So I'm going to give you a basic mission overview here. So people have done a lot of pretty crazy stuff on motorcycles. And I was pretty surprised to learn that a lot of it is done by trial and error. There's not a lot of engineering that goes into it. So what we're planning to do is use engineering to push what's possible with the motorcycle jump. So before I go on, one thing I want to highlight is some of the things we're going to talk about are covered by an NDA. So you will see some vague language and depictions. Just keep that in mind. So here's the mission profile. So there's an initial approach and takeoff. Just the motorcycle itself will not be enough power. So there's going to be some sort of extra power added. It's going to reach an apogee and then glide down. In that glide slope, you're going to see some sort of autonomous controlled system, just so it's very stable, very easy, very repeatable. And on the landing, we're looking to land as much like a motorcycle as possible. So some requirements for this project. One thing to highlight is we want this to be as repeatable as possible. There's lots of training that goes involved with this. There's human factors, and there's lots of data. This has to be repeatable. We also have a safety-driven design. A lot of this, we're representing CU Boulder, and we're putting lives at risk. So we want to be sure that everybody is safe at the end of it. I'm going to hand it off to Brian. Oh, you already have the mic.
Hello. Yeah, so as with any complicated aerospace project, we need an org chart to know what everyone's doing. But first of all, here's our lovely faces and our people. Yeah, so of course we have the project managers at the top, kind of organizing generally. But we also wanted to divide into sub-teams based off of everybody's interest and or previous experience. So we have the 3 teams of Aeromech and Test and Safety, and then the Avionics. So each team deals with a different aspect of the vehicle, utilizing our unique experiences in undergrad and whatnot. So some stakeholders, of course, we have the writer who came to us with this project with really, this has been a goal of his for a while. And so we're basically implementing his dream. And we're taking our engineering experience here at CU and applying all the engineering principles among our team, as well as using the engineering experience of our faculty advisor, Hank Scott.
So one important part of our development, the initial stages, was just outlining our fall critical path. And so just to get a better understanding of our milestones and deliverables and goals for this project. And so starting with the kickoff, which we have already completed at this point, we met with our stakeholders and held our initial meeting where we discussed some of the challenges, requirements, as well as we received some feedback on some of our basic and initial napkin paper, if you will, designs. And so next we're now transitioning into our PDR, where we're going to focus on kind of 2 theoretical design spaces, if you will. And so this will include 3 sub-level groups within our team, Aeromech, Avionics, and Test and Safety. And then from there, we'll be going into prototyping, which will focus down on 2 viable design spaces, and we'll do more of an in-depth analysis, testing, and also focusing on mitigating the risks that we have control over and don't have control over. And so lastly, with our CDR, we'll kind of look at our final design space, which will kind of include some of our final designs, look at different models, and again, with the risks, and then talking about our plan for the spring semester moving forward.
Hi, I'm Katie. I'm serving as the Test and Safety Lead, and I'm going to talk to you about the first milestone that we've accomplished. So we were able to hold a meeting with our stakeholders and do an initial design review. We came into this meeting with 8 preliminary design concepts that included different propulsion methods, different aerodynamics, and different descent and landing concepts. We were able to narrow these down towards 2 primary designs that we are still finalizing, and we received really good feedback from our customer. We learned that they want a fixed wing motorbike that will land on a runway-like landing, and the ideal takeoff speed will be 120 miles per hour, and the ideal landing speed will be 70 miles per hour.
Awesome. I'm Tim. I'm the aerodynamics lead. So I want to talk a little bit about where we are right now and how we're taking this project out into the future. So the first thing that we need to do is we have an idea of what our stakeholders want. So we need to validate those ideas and make sure that they're feasible design spaces. So those 2 design spaces that we talked about a little bit earlier, we're currently performing trade studies. And so we're considering everything that could possibly produce lift, whether that's speed chutes, fixed wings, propellers, auto rotation, even powered lift or thrusters, propellers, or rockets are considered. Another big part of this, because there's humans involved, is testing identification. We want to make sure that the humans are trained and tested and know what they're supposed to do when the mission is performed, and then also that our aircraft performs the way we desire. So one of the biggest parts we're working on right now is we have severe interest in a fixed wing design from our stakeholders. So we're performing actual wing design to try to get an idea of how the design will look like based on our parameters for our mission. Also, we're looking into other lifting device analysis, whether that be for testing or training, or for other methods such as the actual mission. If that were powered thrust, for example, we're looking into those as well right now.
All right. I'm Chandan, and I'm the aerodynamic lead. We shortlisted 2 rockets and jet engines after a kickoff meeting reviews. And we're currently conducting trace studies on rockets and jet engines based on different criteria such as availability, thrust, mass, reusability, controllability, etc. We're also developing propulsion models in OpenMotor and MATLAB for rockets. And also we're considering the commercial off-the-shelf products for jet engines to support the trace studies.
Hello, I'm Marius. I'm the simulation lead. And in terms of simulation, so far we've done 3 degree of freedom simulations for all the initial concepts that we came up with. So for example, here's a proposed trajectory for a propel takeoff with a steady glide slope to the end. And we've also recreated previous jumps in our simulations and gathered data from those, like drag coefficients. And right now we're working on integrating environmental and operational uncertainties into our simulations.
Hi there, I'm Shooting and I'm the avionics lead. For avionics for hardware, we're currently looking at we're currently selecting sensors for sensor suite as well as power, and we are focusing on wireless communication in order to maintain communications throughout the whole flight.
Hi, I'm Nico. I'm the electrical and controls lead here. So one of the advantages of using aerodynamics and engineering principles to design and inform the design of a motorbike is that we can add aerodynamic control surfaces. And in doing so, we can control the trajectory and orientation of the bike throughout the jump. And in particular, we're concerned about the descent and landing, and we can control the motorbike to actually land like an aircraft along this glide slope path, and really just follow that and ensure the safety and land on the desired target that we'd like. And in order to validate this design, we will follow some of the software design guidelines set out by DO 178C. That's typical for safety critical systems for crewed aircraft. And in particular, that means using model-based design and requirements traceability, as well as we will do some software in the loop testing with our simulation models, and as well as hardware in the loop testing once we get to that point.
All right, I'm Tyndall. I am the human factors lead on this project. So my job mainly is thinking about the person on the bike and making sure they're going to make it out of this, be able to keep doing all the fun things that they like to do. So the main things that we want to think about in this is going to be when we leave the jump and when we come back down. So there's a lot of forces going into this person's body. There's a lot of acceleration. We're going to need a lot of speed. So that introduces a lot of G-force, which can lead to him changing his posture. And then that could affect the aerodynamics and also his own safety. There's also the G-forces can have physical effects such as G-lock, which is loss of consciousness, or visual impairments. Okay. And then landing, what goes up must come back down. So he has to come down in a way that's going to be safe for him. So there's a bunch of different ways that we're looking at making that safe. And Becca can talk a little more about that.
Hi, my name is Becca, and I'm going to go over the different safety methods that we are looking at for this project. So first of all, when we want the vehicle to land in a way such that the impact of the landing doesn't harm the vehicle or the rider. And so we are looking at different methods for both slowing down the descent and making the landing shock absorbing. So the methods we're looking at for slowing down the descent include retropropulsion, rotors, and then things such as parachutes, paragliders, and drogue chutes. For the landing, we're looking at options that are separate from the bike. So resi ramps, or resi, which is a material that absorbs a little bit of shock. We could have it on the ground, and also crush foam, which would also allow us to have some shock absorbing material. For the bike itself, we're looking at hydraulics and shocks, which a lot of motorbikes have built into them. And then we're also looking at using seat crush foam, so extra foam to for underneath the rider, and then a roll cage, which would go around the rider, meaning that if something bad happened, they would be protected from the outside.
I'm Corey. I'm the structural lead, and I'll be talking about some of the difficulties and challenges that we are anticipating. So our main challenge, I think, is going to be communication. We have a big team here, as you can see, and also we have many interests that we need to manage, including the rider, who doesn't have a great engineering grasp, and the college, and all of us. Furthermore, we have some variable deadlines, so we don't know how long the manufacturing of the bike is going to take, and that really determines how quickly we need to get everything done. So that's a big challenge in the future. And this is all confidential, which just kind of adds a level of complexity to everything. Yeah.
Okay, we have 1 minute, one question. Burning question up.
Yes, I see a hand up. Any other questions? They're pretty cool. We can get through a lot more.
You're answering the question.
Thank you so much.
Our evening. Thank you everyone for coming. If you are here as of interest for the program next semester, please come by and talk to me. Again, anybody in the course, if you'd be willing to take the pizza boxes to the dumpster, I would really appreciate it. Otherwise, Joey will have to do it. Thank you all. Have a great evening. Please take your trash out.